All right, good morning everyone. Welcome to our new classroom. So, we're going to pick up with torque, chapter 7. All right, so starting off, what is torque? It's probably a fairly familiar word to you. You've probably heard it in one context or another, maybe working with tools, maybe working with cars. But I'm sure all of you have heard of torque in one fashion or another at some point. So really the question is, what is torque? How is it defined physically? Well, put simply, it is the rotational equivalent of force. So the way we studied force in chapter 3, push on a box, it moves. Similarly, if you push on a wheel, it spins. Forces cause accelerations, torques cause rotational accelerations. Torque is a vector. So that means direction matters. But we're going to deal with very simple cases. We'll deal with one-dimensional torque. Which means it's either positive or negative. And how do you determine that sign? Well, we have simple conventions. Clockwise is negative, and you can remember that because the right side points down. Clockwise is negative. And then that makes counterclockwise positive. And of course the right side points up. And I'll usually abbreviate these as either CW or CCW. Now the amount of torque depends on three things. And I usually make an analogy to opening a door. That's a simple example of torque that we all probably experience on a daily basis. Well, of course, if you push harder, you apply more force, of course, that's going to give you more torque. Another thing that impacts torque is where you push. When you open a door, do you open near the hinges? No, you always open opposite the hinges. You want more length. You can go try to open a door near the hinges. You have to push much harder to make up for that short distance there. You push near the far edge of a door, it's easy to open. More length, more torque. And then lastly, we push at a right angle. That gives you the most torque. If you pushed on a door at a slight angle, it doesn't work as well. And if you push directly on the edge of a door, towards the hinges, you don't swing the door open at all. You're pushing right directly on the edge, you get zero torque. And if we put all of these things together, we get the equation for torque. Torque is given by the Greek letter tau. And it's equal to force times length times the sine of theta. But we don't really use any trig in here. So practically speaking, we will just use torque as force times length and assume or make sure that our angle is 90 degrees. So torque is simply force times length when your angle is 90 degrees. Well, now that we've got an equation, let's do what we always do. Let's look at the units for torque. The units of torque must be the units of force times the units of length, which is going to be newtons times meters. Oops. Or foot-pounds, if we wanted to use British units. And I know we've seen Newton meters before, and we've seen foot-pounds before. These were the same units that work had, but there's a subtle difference here. Newton meters for torque are a vector quantity. Newton meters for work is a scalar quantity. This really comes from how you multiply them. This sine theta, this comes from what's called a cross product, but that uses vector calculus. That's a little beyond what we'll do in this class. So there's a lot of subtle details there that are lost. We're going to simplify it as we usually do. But there really is a difference. Even though they look the same, there is a difference between those Newton meters of torque and the Newton meters of work. This is why when we touched on work and I said you've probably heard of foot-pounds, it's not really the same foot-pounds. Foot-pounds of torque are different than foot-pounds of work. And lastly, because torque is a vector, we can sum it up just like a force. We used to find a net force by summing up all the forces. We're similarly going to find a net torque by summing up all the individual torques. And practically speaking, you can set this up as your net torque is going to be all of your counterclockwise torques. Remember, those are positive, and then minus all of your clockwise torques, because those would be negative. This is how we will compute a net torque. And that's where we'll stop for this first video. We'll pick up from there in just a second.